So, little apologies there. So, once I stopped the recording to erase the whiteboard, I accidentally pressed the button that stopped the recording altogether instead of the button that just pauses the recording. So, if this equation pops up on 2 videos, you know why. Because I pressed the wrong button and it stopped recording altogether. But we're gonna ignore that. So, what we have over here is an integral sum definition of our original sum. Now this looks much more pleasant. It's now formed with integrals and not logarithms and not the tail of Riemann zeta functions and blah blah blah. But we still have this thing right here. And if you noticed, I changed it up a little bit, because before we had x to the k up here, but over here we have x to the k plus 1, and then over here we divided by x. Now what we're going to do is, we're going to use that x to the k plus 1 is actually an antiderivative. I mean, x to the k plus 1 over k plus 1 is an antiderivative. It is the antiderivative of x to the k. So what we're going to do, we're going to denote this as like s. Maybe S sub n. And what we're going to do, we're just going to do some stuff with it. Sn is equal to an integral from 0 to, I think it was x, of the sum k equal to 1 up to infinity of t to the k sigma n of 1/2 1 over k dt. Now, the inside sum is actually a sum that Cornell solved in his book Almost Impossible Integral Sums in Series, where he proved it by induction. And we're going to have a whole entire section dedicated to this sum, because it's a pretty epic one. See you there. Now, in his book, he conjectured that this sum, including the elementary symmetrical polynomial, is equal to -1 to the n over n factorial times the natural log to the nth power of 1 minus t over 1 minus t. And he proved this by induction. And we're going to follow his footsteps. So the first thing that we're going to do is we're going to multiply both sides by 1 minus t. What this will bring us is that the sum k is equal to 1 up to infinity of t to the k, of course, and then we have 1 minus t sigma n of 1/2 all the way up to 1 over k is equal to -1 to n over n factorial times the natural log to the nth power of 1 minus t. The next thing we're going to do is we're going to split up this sum right here. We're going to split up, in fact, into 2, one telescoping and one, well, not telescoping. So what we have over here is the sum. Okay. It goes from 1 up to infinity of x, or should I use t actually? T to the k sigma n 1/2 all the way up to 1 over k minus 1 over here, and then we have minus t to the k plus 1 sigma n of 1. Okay, this is the first part, and then it's going to add sum k is equal to 1 up to infinity of t to the k over k sigma minus 1. My handwriting is getting a little bit sloppy, but hope you guys can understand. This is a telescoping series right here, and this thing evaluates to 0. That's right. 2/3 of this entire expression just evaluate to 0. And all we have left is this. And once you realize that t to the k over k is another antiderivative, and it's equal to the integral from 0 to t of, say, for example, s to the k minus 1 ds, you get an idea of how to solve this. This is actually equal to integral 0 to t. We should probably do a sum first. K is equal to 1 up to infinity. S to the k minus 1. Sigma n minus 1 of what? 1/2 dot 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 1 over k minus 1 ds. Gotta get up. Now, if you'll notice, this sum we have right here is actually exactly equal to this first original conjectured sum right here, but just evaluated at n minus 1. So we're just going to plug in this, but evaluate at n minus 1. And what we have is negative 1 to the n minus 1 over n minus 1, factorial, integral from 0 to t of natural log to the nth power of 1 minus s over 1 minus s ds. Oh, never mind. This is supposed to be n minus 1. So what we have here is basically a standard integral problem. You can use u substitution, u equals natural log of 1 minus s, whatever you like. But whatever you get is always going to come out to negative 1 to n minus 1 over n minus 1 factorial multiplied by negative 1 over n natural log to the of 1 minus t. If you combine this, we got this is just n factorial. And negative 1 turns into this. We have now proven that this is true, meaning that this is also true, meaning that we found the solution to t to the k times the elementary symmetrical polynomial, which also means that the symmetrical polynomial is the generating function of this natural log of 1 minus t over 1 minus t times negative 1 to the n over n factorial. Meaning that we can plug this in to the previous, you can say, slide, where we solve for s sub n. And if you need to refresh, well, I mean, you're going to have to refresh because I'm going to erase the whiteboard, but yeah, whatever. See you there. So, I might need to tilt the camera a little bit so you can see. This is the result that we found earlier. Right? This negative 1 to the n times natural log to the n power 1 minus t over 1 minus t. This is conjectured to be true, and it is true. Next, we're going to move on over here where we find the exact same sum, so we're just going to plug in this to that. And then we're basically actually pretty much done. Actually. I know, surprising, right? We have negative 1 to the n over n factorial times an integral from 0 to x of natural log to the nth power of 1 minus t over 1 minus t dt. This, once again, is another basic integral. You can do like u equals natural log of 1 minus t, whatever you like. But it's going to show up as like, but the end result is going to be like this. Negative 1 to the n over n factorial multiplied by, okay, we have a negative 1 over n plus 1 times the natural log, the n plus 1 power of 1 minus x. Okay, now this combined together forms n plus 1 factorial. This plus this negative 1 to the n and negative 1 added together is going to be negative 1 to the n plus 1. And over here, we have the value of Sn, and we're basically just done. I mean, what is there left to do? Plug this in and evaluate the integral? That's not too bad, right? Right? Actually, I probably won't erase this because, never mind, my eraser fell. There we go. And so, what we have here, our big sum that involves the elementary symmetrical polynomial and the tail of the Riemann zeta function is going to be equal to an integral going from 0 to 1 of natural log to the p minus 1 x. Natural log to the n plus 1 x. So, 1 minus x over x. 1 minus x. And then, plug in, this is a constant multiplier, so negative 1 to the n plus 1 over n plus 1 factorial. Now, at first glance, this integral right here might be a little bit scary. Because, yeah, try whatever you want, it's not going to work. But luckily, we have the beta function. I'm going to do a short, should I do a review of the beta function? Yeah, whatever. So, basically, the beta function. Or, I should probably write it as this, because this is actually the Dirichlet beta function, which is a completely different thing. So I'm just going to write it like this, of x, comma, y. It's going to be equal to the gamma function x, gamma function y, over gamma function x plus y. This beta function has shown up many times in all over, physics, whatever, math. And it's going to come in handy today because we have an integral definition, which is going to be an integral going from 0 to 1 of, so, t to the x minus 1. 1 minus t to the y minus 1 dt. This might seem a little bit similar to this, but it's not exactly quite because we have these natural log terms. But luckily, once we take the derivative of x and y, we get natural logarithms. And that's exactly what we want. So, what this is going to be is exactly equal to, not really exactly, but whatever, negative 1 to n plus 1 over n plus 1 factorial. We have the limit. You don't really have to do limits. You could just evaluate, but whatever. X approaches to 0. Y approaches to 0. Of, over here, since we're going to count the t terms is with respect to x, so we have the partial derivative with respect to x, p minus 1 times. And then we have the partial derivative with respect to y, n plus 1 times. And so add these two numbers up, we have p plus n on the top of the beta function of x, comma, y. And we're done. The big scary sum with the elementary symmetrical polynomial and the tail of the Riemann zeta function all multiplied by 1 over k plus 1 evaluates to negative 1 to the n plus 1 over n plus 1 factorial times the limit as x approaches to 0, y approaches to 0 of the partial p plus n over partial x to the p minus 1, partial y to the n plus 1 of beta of x, comma, y. And that is the result. This is the most amazing result I've ever seen in my entire life. It is so, it looks really cool. You just have to admit, this looks really cool. It's complex, but it's easy to understand. And it's the solution to this massive sum. So, that's it for this video. Or should I say 2 videos, because my hand misclicked. But whatever it is the end of this sum. And I'll see you guys, the next time I record, basically. See ya!